Hey everybody, Dr. A here, and in this video we're going to be exploring an example dealing with distributed loading. But before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. Alright, let's get started.
In this example, we're being asked to compute the moment about point A in the diagram given. So let's take a look at what we have here. We have this vertical member that's attached to the ground at point A, and this member is 12 feet tall, and we have this distributed load acting on the member. Now, at the free end of the member over here, up at the top, the load intensity is 20 PLF. And then at the base here, the load intensity is 50 PLF, and this is a linear variation. Okay, so the first thing I'm going to do is I'm going to note that a PLF, all that is pounds per foot. The L means linear, so sometimes we say pounds per linear foot, but all that means is pounds per foot, okay? So the next thing I want to recognize, this is a trapezoidal shape. So it's pretty similar to the previous example that we saw, okay? A trapezoidal shape. And remember, anytime you see a trapezoidal shape, you should think, okay, all this is a rectangle and a triangle. So I can easily break this into a rectangular shape, as you see here, and a triangular shape that we would see here, okay? And then what we would need to do is make sure we can recognize the load intensity of the triangular portion. So the intensity of the rectangular portion is 20 PLF whole way through. What about the intensity of just the triangular portion? Well, of course, that's going to be 30 PLF, okay? Because the total intensity is 50 PLF, and we see that down here. Okay, so we're ready to tackle this. So under the solution, the first thing I'm going to say is, recognize the simple shapes. Okay, the next thing I want to recognize is that the rectangular portion is going to have its own equivalent point load, and the triangular portion is going to have its own separate equivalent point load, all right? And each of these point loads is going to have its own moment arm down to point A. So again, it's a similar in concept as what we saw in the previous example, except here we're being asked to compute the moment. We're not really being asked to compute the total equivalent point load and its location. We just want this moment, this tendency of rotation about point A due to all of this loading here, okay? So the first thing I'm going to do is I'm going to compute the equivalent load due to the rectangular portion. I'm going to call this F rect, and of course that's going to be 20 PLF, or 20 pounds per foot, times 12 feet. So that's going to give me 240 pounds, and of course that's pointing to the right. And then we're also going to have the equivalent point load due to the triangular portion. That's going to be 1/2 base times height. So we're going to have 1/2 times 30 pounds per foot times 6 feet. I'm sorry, times 12 feet. What was I thinking? Times 12 feet. All right. And so what do we get here? 6 times 3 is 18. So we should get 180, right? So yeah, 6 times 30, 180 pounds. And that's going to be pointing to the right. So what does our equivalent system look like? Well, here it is. Here's point A down here. And we have F rectangle, which is right here. That's 240 pounds. And then we're going to have F triangle, which is right here at 180 pounds. Now, what are these relative distances? Okay, we got to ask ourselves that. Well, remember, the equivalent load, or the location of the equivalent load of a rectangular portion is always right in its middle, okay? So that means that the 240 pounds is located at a distance of 6 feet and, of course, 6 feet from the top, right? So no question there. What about the equivalent triangular load? Well, remember, it's always 1/3 of the distance from the back face and 2/3 of the distance from the tip, okay? So what is 1/3 and 2/3 of 12 feet? So 1/3 would be this distance right here. Ooh, this distance right here, which is 4 feet. And then, of course, 2/3 is this distance here, which is 8 feet. Okay. And so here are our moment arms. The moment arm for the 240 pounds, which is coming from the rectangular portion of the load, is 6 feet. And the moment arm for the 180 pounds, which is coming from the triangular load distribution, is 4 feet. So I'm going to say the moment about A, and we can call counterclockwise positive, is going to be the sum of all of the moments about point A, counterclockwise positive. And so that would give us a negative 240 pounds times 6 feet, and then minus 180 pounds times 4 feet. And of course, the moment about point A, the total moment about point A, is going to be, let's punch that through, 240 times 6, and you combine that with 180 times 4, and I get 2160 pound feet. Now that's a negative, right? Because both of these forces are causing a clockwise tendency of rotation. So so that's going to be negative, and or we could just put a clockwise symbol right there. And then that's our final answer. Okay, so again, you got to be careful because this problem, even though it's geometrically very similar to the previous example, it is asking for something different. It's asking for the moment about point A, whereas the previous example asked us the location of the equivalent point load. So read the directions carefully on all of